a small change in crack length. G is also referred to as a crack extension for force, and is given by G is equal to d pi over dc, with the minus side. Okay, so that pi is the total potential energy. The potential energy is difficult quantity to visualize. In the absence of external traction, that means we are applying the displacement controlled loading condition or boundary condition. So if there is no load or traction, it is difficult to visualize. The potential energy is equal to the strain energy stored instead. So in our case, the pi equal to US. So we can substitute that US instead of pi. So G is equals to dUS over dC minus of. With the displacement boundary condition, only G has unit of joule per meter square or Newton per meter. So as we have seen, US is given by US is equal to pi c square sigma square over E. Therefore, G is equals to 2 pi c. Integrating this U with dc, we can get 2 pi c sigma A square over E. Crack growth occur if G exceeds a critical value GC. GC is the critical value of energy release rate, which is the fracture toughness of the material. So G is equal to GC for perfectly brittle solids, or GC is equal to 2 times gamma F. This equivalent to Griff's criteria. Okay. So it is better to understand the basic of fracture with fixed displacement boundary condition without any surface traction. So a relation between K and the G. In spite of the fact that G has more direct physical interpretation for the crack growth process, usually we work with K as it is more amenable to theoretical competition. K can be related with G by the following formula. So K is equals to GE for the plane stress condition, and for the plane strain condition, K square is equals to GE over 1 minus mu square, because in plane strain, the instead of E we have E over 1 over, yeah, let me write it. Okay, screen pointer. Okay, green. Okay, so E is equals to, instead of E we use E over, okay, I can say 1 minus mu square. So because of that, this is substituted with this value for plane strains. Okay, the stress fields at the crack tips. For the body subjected for far field biaxial stress. Look, here there is biaxial stress. Okay, stress in the Y, stress in the X. And there is a crack here with a double ended through crack, 2C. Okay, so for the body subject to biaxial stress, sigma naught with double ended crack of length 2C, the stress state is given as for mode 1 loading. Actually, this is for mode 1 loading. Sigma xx is equals to K1 over radical of 2 pi r. Cos theta over 2 times 1 minus sine theta over 2 times sine 3 theta over 2. This is taken as equation number 1. For yy, The same equation also holds true. And for xy, that is for the shear case, we have only, actually not the same, sigma yy has 1 plus sine theta over 2 here. Here 1 minus sine theta over 2, that is the difference. And here, instead of this 1 minus or 1 plus, it is simply sine theta over 2. These three formulas are there. So sigma ij is proportional is 1 over radical of r. Okay, so the inverse square root of r, that is singularity at the crack tip. The intensity of the singularity is captured by Ki, the stress intensity factor. This Ki is stress intensity factor, or Ki is the scaling factor for the singularity. This is the meaning of Ki. As no material can be withstand infinite stress, in ductile material plastically will intervene. Clearly, the solutions are not valid exactly at the very near to the crack tip. At theta is equal to 0 and r approach to infinity, the stress sigma xs and yy should tend to sigma naught, because here k1 is there. When gamma, this r approach to infinity, and the theta 0. Theta 0 means cos 0 is 1. 1 minus sine 0. Sine 0 is 0. This sine 0 is 0. This part will get 0. So 1 times 1, 1. So k1 over, we have left k1 over 2 pi r cos 0. So cos 0 times 1, we can get 1. So we have left k over this thing. Here also the same. This part will get 0. Okay. This part will get 0. This is 1. This is 1. And gamma approach to infinity means k over infinity. Means just 1 over infinity means it is almost 1. So finally, what that sigma naught? This is not the case, as seen from the equation 1 and the 2. This implies that the equation should be used only close to the crack tip, with little error, or additional terms must be added to the equation. Okay. So understand the stress field equation. So this sigma xx, the stress field equation, sigma xx is ki over 2 pi r cos theta over 2, 1 minus sine theta over 2, sine 3 theta over 2, which implies sigma xx is equal to k1, taking this as a function of theta. This quantity is as a function of theta. So f of theta over radical of 2 pi r. Again, this is also a function of r. So we can put it as f of r theta. Okay, so sigma x is equal to ki f of r theta in terms of function. So this ki indicates mode 1 loading. Okay, and the y is shape factor, the shape factor related to geometry. And sigma naught is the stress, or the far field stress, and pi c is the half crack length. So this is the relation for ki. So ki is equals to y times sigma naught radical pi c. Okay, so ki is the strength and intensity factor, or quantifies the magnitude of the effect of stress singularity at the crack tip, according to as given in the Antonio C. Fisher Cribb Introduction to Contact Mechanics, Springer 2007, and that K has unit of Newton per meter square. That is stress Newton per meter square times radical of meter, or Pascal radical meter. Typically it is megapascal radical meter or Pascal radical meter. So quadrupling the crack length is equivalent to doubling the stress applied. Hence, K captures the combined effect of crack length and loading. The remaining part in equation 2 is purely the location of the point in r and theta, that in the coordinate. Note that there is no crack tip radius rho in the equation. The assumption used in the derivation of equation 1 to 3 are rho is equal to 0, infinite body, biaxial loading. The factor y is considered in the next page. So that shape factor y, okay, so how we can, it's obvious that geometry of the crack and its relation to the body will play an important role on the effect on the fracture. The factor y depends on the geometry of specimen with the crack. Y is equal to 1 implies for the body considered in figure 1. This is the figure. In this case, y is equals to 1. Regions for where additional strain energy is released, these are okay, double-ended cracks in infinite body. Y is equal to 1.12 for the surface crack. The values of y is greater than by 12% for the surface crack as additional strain. Y is equals to 2 over pi for embedded penny-shaped crack, and y is equal to 0.713 for the surface half penny cracks. Region of K dominance. The crack tip field consists of two parts. One is singular part, which blow up near the crack tip, and the second is the non-singular part. The region near the crack tip, where the singular part can describe the stress field, is the K dominant region. This is the region where the stress intensity factor can be used to characterize the crack tip stress field. In material, where the crack tip plasticized zone is smaller, then the K dominant region also called the small scale yielding, that is SSY region. Concepts of the linear elastic fracture mechanics can be used with the little error. Fracture toughness, that is ruins K based. One of an important goal of fracture mechanics is to derive the material parameter, which characterize cracks in the material. This will be a key to yield stress sigma in the uniaxial tension test. Sigma y is the critical value of stress, which if exceeds sigma greater than sigma y, then yielding occur. The criterion or critical condition for fracture in mode 1 can be written as K1 is equals to KIC. This is critical fracture toughness, where Ki is the critical values of stress intensity factor, and known as fracture toughness. Okay, this K1I is a fracture toughness. K1C is the material property, like yield stress, and can be determined by the different materials using standard testing methods. K1 is a microstructural sensitive property. The focus here is local crack tip regions and not global. As the case of Griffith's approach, all the restrictions or assumptions on K will apply to K1C. Okay, that materials are linear elastic behavior. That means no plastic deformation or other non-linear behaviors. Inverse square root singularity exists at the crack tip, and the K dominant regions characterize the crack effect. So sigma x is equal to ki over f of theta over radical